Hello, I'm Narayan Kandel. Today I'm going to present my work on enhancing performance of distributed neural network with GNN bundle. In this project, I work under the supervision of Lily Su and Rosate. The background for this is nowadays with the introduction of ChatGPT, there are a lot of interest in AI, even more all the researcher and industry from uh, manufacturing, medicine, art, history, like a lot of different diverse field want to explore how AI does in their field, and due to that, there is a lot of resource demand, which resulted resource shortage. Generalized neural network being one of the choice for the distributed neural network training. We want to improve it to have better control over machine utilization and optimize its performance within a GNN during backpropagation. The time required for each iteration is equal to the time for the weakest node due to the aggregation of loss required at the end of every iteration, which we can see in this block diagram. So the research question that we have is, can we improve that time, and then can we improve resource utilization by throttling number of node when we run the training. In order to experiment with our hypothesis, what we did is we adapted the notion of training with the restricted number of nodes, and we enhanced fit function to accept extra parameter called node number, and then we extracted data and then perform training and weight synchronization on those selected node only. At the end of the training, we redistributed weight among all the nodes so that all the nodes will be ready for the evaluation purpose. When we want to use just one node, we do not need to do any communication at all. So we have implemented a special case as well. The result for our experiment is shown on two plot. First plot shows the performance on data classification task. In theory, what we expect is when we halve the resources, we expect its execution time to go by 2 times, but that does not happen normally, because in parallelized system there is 2 time, that is, one is serial time and another is parallel time, and then when we add resource, we only improve parallelized time, like we only can break down parallelized time, not the serial time. So with that in mind, let's look into the green line, which is the time for training 10K classification data. When using 100% resources, we get 6 seconds of training time, and when using 50% resources, we get 6 seconds of training time, and for 30% resources, we get 7 seconds, and for 20% resources, we get 8 seconds. So here the plot does not follow what we normally expect. Also, the plot is consistent among higher data, like 100K data and 1 million data. So it is quite surprising. So by reducing the number of nodes we want to use, we can actually improve the resources, and then later we can do other task on those free resources. So that is the notion of our experiment. This result hold true in MNIST dataset as well. In MNIST, we train for two dataset. Smaller one contains 60K image row, and then bigger one contains 540,000 image row, and then the pattern hold true for both. For the smaller MNIST, time when using 100% resources is more than time when using 50% resources. The reason for that is that when we have large number of node, there is also communication time, which might add extra burden to overall network. So the highlight is absent of anticipated linear correlation between the node count and time, as we expect in general parallel system. This is consistent among both. So in conclusion, having a control over active number of node will be helpful to achieve better time and resource usage by utilizing fewer powerful node, or even powerful GPU node instead of cluster of 100 of CPU node can improve training time, and hence we can use remaining unused resources for the other purposes. Yeah, that's the conclusion of our project. I would like to thank Hugo Watanabe for his constant support during this project, and I would also like to thank LexisNexis Risk Solutions and SVCC Systems for providing me this opportunity to work on this project. Thank you.